All right, well, I propose we start here. So I'm pleased to welcome Professor Lia Vas. She's going to be presenting the second of our 3 talks this spring in the Algebras and Rings in Colorado Springs sponsored algebra seminar series. If you would either mute your microphones or sort of be on your best behavior and maybe ask your dogs to leave the room and various things, that would be helpful. If you have questions during the talk, I'm sure Leah would be happy to answer those. You might either then unmute yourself or simply put the question in a chat box, and I'll be monitoring the chat box as the talk goes on. I'll remind you of the next and final talk in the spring series will be given by Benjamin Steinberg of City University of New York Graduate School. That'll be Wednesday, April 21st, and he'll talk on Cartan pairs of algebras. And now I'm very pleased to introduce Lia Vas, who will speak to us about the graded classification conjecture for Leavitt path algebras and graph algebras. Oh, sorry, graph algebras. Lia.
Thank you so much, Jean. Welcome, everybody. Thank you so much, Jean, for having me here. This is really awesome. And by the way, absolutely feel free to unmute yourself and ask a question in the middle of the talk. Doesn't matter. All questions are always welcome. It doesn't matter if it's at the beginning, middle, or the end of the talk. So what do we have here? We have classification. We like classifying stuff. So let's go straight to it. So everybody has their favorite conjecture. And today we will focus on the one called Graded Classification Conjecture, conceived by Rubric and contemplated by some other people here. So I think it's actually quite fortunate for me that I had Mark presenting on Grothendieck group. I think it was last semester or last spring. And then Rusbech a month ago talking about Leavitt path algebra. So he introduced the, the Leavitt path algebra for me. And I'm sure that those of you that were at Mark's talk know very well what Grothendieck group is. For some of you that may not know what it is, I will just quickly summarize. So you start with a ring and you look at finitely generated projectives and their isomorphism classes, and you can add those by doing direct sum. And then you force the cancellativity so that you can complete that to a group. And that group is called the Grothendieck group. So the question, very, very general question is how well that K0 reflects the properties of R. And in other words, does this equivalence here hold? And one direction better be holding, otherwise K0 wouldn't be much of a functor. So, if 2 rings are isomorphic, of course, their K0s are isomorphic, and we are going to talk about pointed a little bit later. And the converse actually rarely holds. So your rings have to be very, very nice, like fields or matrices over fields or things that are nice and regular like that. So let's look at Leavitt path algebras for a second, and I won't present like a definition of Leavitt path algebra because I think that we will be able to understand the main ideas of the talk without actually caring too much about Leavitt path algebras, because in a way, graph is star of the show here, not Leavitt path algebra. And for those of you, I will just in 3 sentences summarize the idea of what Leavitt path algebra is. So you start with a graph, you form paths, you can concatenate them, so that's kind of how you multiply. And then you force the involution. In other words, you look at the paths going back, And then you put 2 extra spices on top, which are 2 axioms, additional axioms. And for all purposes of the talk, this is enough for you to imagine what Leavitt path algebra is. So let's look at these 2 graphs here. As graphs, they couldn't be any different, right? So here we have no edges at all, right? This here is a nice cycle here, so it has edges. You can think of this as a cyclic graph. This one has a cycle. So as graphs, they're very different, and their Leavitt path algebras are not isomorphic. However, their K0 groups are just a copy of Z. And here we have another graph, which is called the rows, and that's why I have this rows here. So this graph is very non-trivial, of course, and its Leavitt path algebra is also non-trivial, but its K0 group is trivial. So because of these kind of bad properties that we have here when K0 is concerned, we need, before we go to the bad properties, let me just elaborate on how do we know what K0 is. So in general, how do we compute a K0 of Leavitt path algebra? And that's where a graph is the star of the show. So you can start from a graph, and for purpose of this talk, I will just restrict myself to row finite graphs, meaning that you cannot have vertex emitting infinitely many edges. So I will restrict myself to row finite graphs just for the purpose of these talks, but everything that I'm saying is going to hold for any graph. So you define a monoid called the graph monoid, and your generators are vertices, technically elements indexed by vertices, and I'm going to denote that with V in brackets just so that we imagine really K0 there. You can form K0 using the idempotents, and vertices are idempotents, so this is kind of class in K0. So, so these are your generators, vertices, and you impose a single relation, single if graph is row finite, which is saying that V is equal to this sum, where E are edges V emits, and RE are ranges of these edges. So we are going to see Leavitt path algebras only on this slide, and I'm going to elaborate why this relation and not some other. So, so one of the Leavitt path algebra axioms, one of these 2 spices called Kunz-Krieger 1 and Kunz-Krieger 2. So the second one is saying that this here is equal if you remove the brackets. So your V, I should also mention that V emits finitely many edges and non-zero edges. So for those vertices, we impose this, this relation. So why this relation? Because if you remove these brackets here, then you are looking at Kunz-Krieger number 2 axiom. And then you can go with brackets like inside. And these 2 things, E star and E star E, are the same thing if you're looking at the isomorphism classes, because the finally generated projective generated by E star and E star E, they are isomorphic, because left multiplication with E and E star are the isomorphisms, going back and come one way and the other way. So that's why this second equality here holds. And this last one is Kunz-Krieger number 1. So you see that's the relation that Kunz-Krieger axioms impose to hold. And that is the one that we use to form that graph monoid. Okay, so this monoid, as we have seen, has nothing to do in particular with Leavitt path algebra. These axioms are kind of present, but you can form it using graph only. You don't need like Leavitt path algebra. And this monoid turns out to be isomorphic with the isomorphism classes of finally generated projectives. And then when you complete to Grothendieck group, then you have a Grothendieck group of the graph, being exactly the case 0 of Leavitt path algebra. So now when we understand how to form this graph monoid, we can actually see why Grothendieck group of this of Leavitt path algebra of this rows is going to be 0, because let's see what is our relation here. So here we have V that emits two edges to V. So the relation is that V is equal to V plus V. And then, so this is the relation in the monoid. And then when you force cancellativity, then one V gets canceled, right? So pretty much your one and only generator in the group is going to be V is equal to 0. So that's why the whole Grothendieck group is 0. Okay, so this bleak situation that I was describing, how different graphs give you the same Grothendieck group. Who comes to save the day but this knight in shining armor called grading? So Leavitt path algebra is also graded. And what does that mean? What is a graded ring? It's a ring that you can chop in many pieces that are going to correspond to group elements. So you can decompose that ring like this. And then this is your natural requirement that kind of multiplication in the group agrees with the multiplication in the ring. So if you take two elements of the ring, each sitting in two different components, and you multiply them, you end up with an element that is exactly labeled by the product of these two starting group elements, so starting two labels. So, so the name of the game in the world of graded rings is that you take your good old ring theoretic property, and then you replace in it the word element with homogeneous element. What is a homogeneous element? So it is an element that comes from a component. So in a graded ring, every element is sum of elements from possibly different components. And if your element is actually sitting in only one of them, it's in R gamma for some gamma, then it's homogeneous. So for example, how do you define graded regular? You take your definition of von Neumann regular element, which is X is von Neumann regular if there is a Y such that X is equal to X, Y, X. And if that holds for every element, you say that ring is von Neumann regular. What would be graded regular? For every homogeneous element, you can find another homogeneous element Y such that X is equal to X, Y, X. And if you are looking at module theoretic definitions, you are replacing word module by graded module, isomorphism with graded isomorphism, and that's the category that you work with. So Leavitt path algebras are naturally graded, just like many other rings are. And in particular, natural grading of Leavitt path algebra is by integers. Because remember how we started with paths and then we imposed the involution, so we have these paths kind of going back. So path of length n, you place in the nth component, star of path of length n, you place in a negative n component. And since Leavitt path algebra is span of these elements here, they are then in nth component if length of p minus length of q is n. So this is very natural grading for Leavitt path algebra. You can grade Leavitt path algebra by other groups, but we'll stick to this like star grading. So, so this is, I think, the only slide where I have some definitions that we will have to go over to understand some main ideas here. So a module is graded if you can chop it in little pieces, and then natural multiplication rule here. So, so that's a graded module. every graded module can be shifted by a group element in this way, right? So here we have that the gamma component of m shifted by delta is m gamma times delta, right? In a way, you are translating everything by delta. So shifts we need in order to understand how a finitely generated graded free module look like. So if you are not in the graded world, let's say that we have n dimensional, let's say, finitely generated free module generated with basis of n elements, right? So that would just be n copies of R. But here, if we want to have kind of rank n finitely generated graded free, then each of these n copies of R may have a different shift. So the reason why we needed to understand that is because we want to understand how does a graded matrix ring look like. So what is a matrix ring? It is an endomorphism ring of R on n, right? If it's n times n matrices. And since here your n-dimensional free module has these shifts are going to play a role in the matrix ring as well. And if you're wondering why is this negative one here, this is something to do with left and right and the way how you define the action and the shift, right? So it's like a technical negative one. We don't have to worry about that. What I want us to understand out of this is that n by n matrices also come equipped with certain shifts if I care about grading of a ring. So, so here we have seen that how does a finitely generated free module looks like, that it has these shifts. So you see the difference between the scenario of one-dimensional free module in non-graded world and in the graded world is that if you are not looking at any grading, or if your gamma group is trivial, then there is just one-dimensional free module. But if your gamma are integers, for example, then we can have many one-dimensional graded free modules, one for every shift. And in general, all these things here may end up being all different, or some are different and some are the same, or they may end up being the same. So just to understand a little bit better what's going on here, let's just look at some examples. So let's take a look at gamma being integers again. And let me just not call it 1, 2, 3, 4, but let me look at the elements of gamma as axon 1, axon 2, and so on. Let me look at those with multiplicative notation. So that when I look at this group ring, I can think of it as Laurent polynomials. So let's grade this ring trivially. That means that I'm just going to put everything in the 0th component and all the other components are 0. So imagine what a shift will do to that, to such a ring, right? So everything is in the 0th component if I don't shift by anything, right? And if I, let's say, shift by 5, then everything is going to be in 5th or negative 5th component, certainly not 0th component. So that's why R0 and R5 are going to be different. And that's actually why Rm and Rn are going to be different if m is different from n. So this is the example when all these things are really different. Let's take a look at another example, same gamma, same ring. And let's grade it if you want in a maybe more natural way, where in the nth component, I'm just going to put scalar multiples of x on n. So when you add all these components together, you kind of get the whole thing. But when you shift that thing left and right, really nothing happens because you still have kind of the same thing, right? So that's why Rm and Rn are isomorphic for every m, every n, right? So that's why we don't have this wide selection of fruit, but again, only one apple. And let's now talk about Leavitt path algebras and graphs and see how the looking at these shifts and the grading, how that differentiates things a little bit better. So from graph standpoint of view, these two things are very different. Like E and F as graphs are very different graphs. This one has a vertex that receives two edges. This one doesn't have such a vertex, right? So as this one has one source, this one has two sources, right? So as graphs, they are very different. Their Leavitt path algebras, on the other hand, as algebras, are the same thing. Why are they M3? So when you are looking at how these Leavitt path algebras correspond to matrices in this case, you count how many paths you have ending in your one and only sink in here. So here we have 0th path, not doing anything, 1 and 2, right? So we have 3 paths all together, so that's why it's M3. And here we also have 3 paths, right? 0th path, path of length 1, I mean length 0, and then this one, and then that one. So also 3 paths, right? So as algebras, they are the same thing. As graded algebras, they are not, because now you are looking at the lengths of this path. So here we have 0, 1, and 2, and here we have 0, 1, and 1. So you see, as graded path algebras, they are not isomorphic. So this is what I meant by, you know, knight in the shining armor saving the day, if you're looking at the grading as well. So then there is this graded version of K0 group, and you literally do the exact same thing that you did before without the grading. It's just that every word projective you replace with graded projective, and then that's pretty much it, right? And isomorphism classes are graded isomorphism classes, but the construction is exactly the same. So here we have a monoid, but it also has a gamma action induced by these shifts. And then you can complete it to the Grothendieck group, and then that's your, Rusbeck calls it graded Grothendieck group, and I prefer Grothendieck gamma group because that group itself is not graded. It's not that it has a grading, it has a gamma action. So I just prefer gamma group instead of graded group. But you can call it whichever way you like, ultimately. So this group, because it has this additional structure, it classifies better. It is more sensitive than the good old K0. So let's just talk about the structure that we have for Leavitt path algebra. So for Leavitt path algebra, our gamma is Z, right? So this gamma action makes it into a Z gamma module. And because I didn't like ZZ module, right? So there is too many Z's going on. That's why you don't want to think of gamma as 1, 2, 3, 4, and so on, but exon 1, exon 0, exon -5, and so on. So, so you can think that it is a module over this, this ring here, right? Okay, so now let's talk about the monoid. Let's try to repeat that construction of a graph monoid that we have seen before. So I also want to start from graph only, and in this case I will start from graph only and gamma. And you can do that for any gamma. We will focus on gamma being integers. So Rusbeck and Huan Li introduced this monoid in their paper published, I guess, a year ago. and they call it talented monoid. So when I think of talented monoid, I always say talented Mr. Monoid. So I call it graph gamma monoid. So there is graph E and gamma there. So these are the two ingredients that went into the mix and the definition. So when you complete this graph gamma monoid when you look at its Grothendieck group, then you get the graph gamma group, and this is the notation I will use. So let's talk about how to compute these two things. And we will concentrate on gamma being just integers. So same generators as before. So your vertices are your generators. Again, I'm just going to restrict on row finite graphs, so there will be just one relation. And if you remember, the old relation was this one without this x here, right? So there was no x there before, right? So now why is there an x there? Why not something else? Why x at all? So the key here is the power of this x, which is 1. So it is x on 1. And that 1 is the length of E, of edge E, connecting V and range of E. So, so because the length of path E from V to range of E is 1, that's why there is this exponent 1 there. So you can kind of see how this relation is going to look if, let's say, V is a vertex and it has, I don't know, 5 paths. So you can go from that vertex using exactly 5 paths, and then you of length, I don't know, K1, K2 to K5. And then it's the relation that is also going to hold in that monoid is going to be that V is equal to sum x on Ki, range of path Pi. So that's the relation that is going to hold in your monoid in that case. So now let's revisit our examples with almonds and cats, and let's see how the gamma monoid and gamma group are going to look like in those cases. So here you have one vertex and you impose no relations whatsoever. So your monoid is going to be pretty much everything that having that x involves, right? And since it's monoid and not group, that's why we have just positive integers here as coefficients, right? So when you complete it to a group, this is going to be your Grothendieck group here. Here you have one vertex, and that relation from the previous slide is telling you that that vertex is equal to x times that vertex. And you can think of that vertex as like 1. So 1 is equal to x times 1. So that means that x doesn't do anything, right? So that means that your action, gamma action, is going to be trivial. So that means that your group is going to be just Z. So you see, only using these very, very down to earth, very basic graphs, we already see the difference that the grading brings to the picture here. And actually, let me just point out that these are exactly the examples where we had just one apple and a whole bunch of fruit from before, right? And let's revisit our rows as well. So if you remember, we have seen that Grothendieck group here is trivial. Well, how is our relation going to look in here now? So here we have V is equal to XV plus XV, right? So you see, this is already, conservativity is already there. You don't have to impose it, and then when you cancel V, there is not going to be anything left. But this is all nice and cancelative, right? So, so that's why you are not going to have 0 when you complete the Grothendieck group. And if you can think of this action of x by as multiplication by 1/2, then this relation here is telling you that 1/2 plus 1/2 is equal to 1, pretty much. And that also gives you an idea why your Grothendieck group is going to be isomorphic to this, like dyadic, whatever, rationals, right? So, so here we see how, again, grading kind of brought something to the mix. So let's now talk about the conjecture itself. So Rubric formed this question. It is now, I guess, 10-year anniversary. So is it the case that for any two graphs, this equivalence here holds? These Leavitt path algebras are isomorphic as graded algebras if and only if their gamma K0 groups are isomorphic as pointed gamma groups. So let's talk about what does that pointed mean next. So far we have seen that your Grothendieck group has some structure, right? We have seen that it is an abelian group because we can add things by direct sum. We talked about gamma action. And this K0 gamma, just like good old K0, has a preorder coming from this relation here. So that holds if P is isomorphic to a summand of Q, right? So if you look at this preorder together with everything else, then you can talk about order units, and that brings this very special element here in the first row of interest here. So what does it mean that R is an order unit? For every element of the Grothendieck group, there is a positive integer such that you can squeeze it like this. And we can certainly understand why this relation here holds, because let's think for a moment just positive elements, right? Like finely generated projective. So every finely generated projective is sitting as a direct summand in R on N for some N, in N copies of R, right? So that's why this kind of holds for positive elements, and then you can think about why it would hold for negative elements, and the argument is very similar. So if you consider your K0 together with an order unit, then that K0 is said to be pointed. So now I want to go over two more examples just to illustrate that both being pointed and having gamma action really matters here. So let's go back to these two graphs that we have seen before, right? And we talked how their Leavitt path algebras are not isomorphic. And then when you compute the gamma Grothendieck group, it ends up being the same thing. However, that order unit is not the same. And here in the powers of x, we see these same 0, 1, 2, right? X on 0, x on -1 and -2, but we do see 1 and 2 there, right? And for the other one, we see 0 and 1 and 1, which are these shifts that appear here, right? So that order unit really matters, right? So they are not isomorphic as pointed, right? The K0s. And here I just want to show you other two graphs and talk about their Grothendieck gamma group, because here the gamma action will really matter. So what do we have here? We have nice no exit graphs, right? So this is like acyclic and no exit. These are good guys in Leavitt path algebra world. Easy to understand, easy to handle. So as graded algebras, here we have this isomorphism of Leavitt path algebra with this algebra here. So these powers of x's in here correspond to this cycle having length 1, and you can see that in here we have a cycle of length 2. And these zeros and ones correspond to lengths of paths that end in a selected but arbitrary vertex in that cycle. So here we have, but not counting the cycle itself. So here we have 0 and 1. And here you can take whichever vertex you prefer. It doesn't matter. Let's take this one and count the paths that end there, but not the whole cycle. So it's 0 and 1 as well. So these are these two Leavitt path algebras. And then when you compute their Grothendieck groups, the order unit is the same, the group is the same, but the action of gamma is not. This one has trivial action and this one has non-trivial action. So really all these things happen. And the reason why I'm telling you, why I'm like insisting on this so much is because when you start thinking of this conjecture, it may seem that different things have kind of the same K0. And that may be just because you didn't incorporate all these structures in your mind. So that's why all these things matter. Being pointed, having gamma action, and everything else. So let me now go over kind of the current state of that conjecture. So around 10 years ago, when he formulated the conjecture, Rubric also showed that for this class of graphs called finite polycephaly graphs. So these are, and I always think of some crazy dragon when I say polycephaly with many heads. So what is that? It's a finite graph such that every path leads either to a rose, to a cycle with no exit, or to a sink. So pretty much you can think of that as if you have finite acyclic graph, and then you attach to every sink either a cycle with no exits or like a rose, right? So that would be a polycephaly graph. So for those, it is known that it is true, the conjecture, I mean. And then in 2014, Ara and Pardo showed that a weaker version of the conjecture holds for finite graphs without sources and sinks. And then more recently, Eilers and Ruiz and Sims showed that the conjecture and as well as its C-star algebra version holds for countable amplified graphs. And I won't go into what those are. I will just point out that all of these things incorporate different graphs. So none of these results is contained in another on this list. So in around 2016, Rusbech and I, we showed the star version of the conjecture, which is pretty much if you incorporate the involution of Leavitt path algebra. So if you look at a ring with involution, then you have another action on your K0, which would be action of Z2. Z over 2Z, right? That's what I mean by Z2. So the involutive version of the conjecture holds for this class of row finite, no exit graphs in which every infinite path ends in a sink or a cycle. So in a way, these graphs are nice because they are no exit, but you know, they're not only finite. So that was like different than some of these results on the previous slide. And so the proof that we had relies on representing Leavitt path algebras as ultramatricial algebra and using properties of graded fields. So in a way, that proof is not Leavitt path algebra proof because we just represented these Leavitt path algebras as ultramatricial algebras over something, and then pretty much it is proof on these ultramatricial algebras. So Leavitt path algebra is in a way like a corollary of this ultramatricial algebra statement. So since it didn't focus on Leavitt path algebras, more recently it was done just before the coronavirus started. And I'm glad that it was done right before, because these first few months, I mean, I couldn't do any math at all. So so in 2020, right, we were looking for more graph oriented approach, not like ultra matricial algebras or anything. So we went back to the talented Mr. Monoid and its structure, and we were looking at certain classes of elements that you can introduce in your talented Mr. Monoid. So previously, Rusbech and Juan Lee, they showed that this relation here is not possible for any positive n. So remember that we have this pre-order, right? So we have this relation less or equal to. Well, if you have less or equal to, you have strictly less than, right? And it is not possible that A is strictly less than x on n times A. So since this is out, what are your possibilities that this is equal for some n, let's say positive n, that this is bigger for some positive n, and that A and x on n A are not comparable for any positive n? So Rusbech and Juan, they showed that this for that every element is in one of these three categories for row finite graphs. And Rusbech and I showed that it is true for all graphs, not necessarily row finite. So, so let's talk about these three classes. So for every element A, you are comparing x on n and A. And if you can find one n that these two are equal, you can find smallest such positive n, and then that A is said to be periodic, right? And here, if you're comparing A and x on n A for positive n's, and you can find n such that A is strictly bigger than x on n A, then you say that A is a periodic. And again, you can then find smallest such n, right? So that you have here strictly bigger. I mean, this is bigger, obviously, right? And so that element is said to be aperiodic. And if x on n A is on a different planet from A, then you say that A is incomparable. So to understand the examples a little bit better, I'm going to go one step back from the monoid, and I'm just going to look at free gamma monoid generated by vertices. So don't impose any relation, just look at a bunch of like vertices, right? And all the elements generated by them. And look at this relation, which is, you can think of it defined by the axioms. So think that from V, you can kind of get to here because that's like, you know, definable by axioms. And then pretty much you can consider your Mr. Monoid to be the equivalence closure of this relation here, right? So let's see how this works in these two examples, right? So here from W, I can get to XW, right? And that means that in the monoid, these two things are going to be equal, and that's why W is periodic. And from V, I can get to XW, right? There is an X here because of this length one path, right? So, but since XW in the monoid is the same as W, V is the same as W, so V is periodic also. So in this no exit graph, everything that can get to a cycle with no exit ends up being periodic. And we will see that this is not like just a example, right? If you are in no exit graph and you can get to these like loops, that all these elements are going to be periodic. So here we have not no exit graph, right? So let's see how the relation here works for W. From W, you can get to XW plus XV. So think of XV as some change, right? So V is, that's why V is bigger than XW, because of this change that we have. So that's why W is aperiodic. And here we have that V is a sink. So pretty much you cannot get anywhere. And that's why X, V, and X square V, and X on 3V, and V, they're all different, right? So that's why V is incomparable. So just to give you a sense of some of these types of vertices, and in general types of elements in the monoid that we can have. If V is a sink, it's incomparable. Pretty much we understand that based on this previous example, right? Infinite emitter can be aperiodic if it's in a cycle, or incomparable otherwise. And cycle in a vertex is periodic if that cycle has no, if there is no exit, right? And aperiodic otherwise. And then you are trying to describe things that are comparable elements. What is comparable, by the way? Comparable is aperiodic or periodic. Aperiodic or periodic, that's comparable, and then incomparable is not comparable. So if you're trying to describe this element in the monoid being comparable, that ends up being if you can get from it to a stationary element. What is a stationary element? All generators are either on cycles or on exits from cycles which contain other generators of B. So you see this, I'm telling you this just to kind of give you a sense of how these things work. What can I do with these like comparability considerations, right? And here actually, I have some statements about descriptions of when is element periodic, when is every element comparable, when is some element comparable, when is some periodic, when is there are no periodic elements in a graph. So all these things play with for all and exists, play with these comparable periodic, aperiodic, whatever. I mean, every combination that you can come up with, there is a nice description via graph for all of these things. So, so I hope that based on this example with cycle with exit and cycle with no exits, I'm hoping that we can kind of see why some of these statements are true. So I think that I already talked about number one. So element is periodic if you can get to a stationary element such that no generators are on cycles with exits, right? There is a comparable element in the monoid if and only if E has a cycle. There is a periodic element in the monoid if and only if E has a cycle without an exit. So, and then there is a statement for periodic, right? So using these things, you can get some nice corollaries. So let me just mention some of them. This monoid then recognizes things like being a cyclic, having cycle with or without exit, being no exit, being row finite, no exit. So it seems that the next level in understanding this monoid better so that you can really maybe get to the conjecture would be to understand the differences between these different types of cycles, like, you know, extreme or not extreme. So that I think would be the main reason why I think the monoid may be of interest. And another corollary is that the main results of this Rusbeck one paper on talented monoid holds without the requirement that the graph is row finite. And yet another one that I thought I should mention is actually related to the characterization of the cross product Leavitt path algebras and skew group ring Leavitt path algebras, which is also a recent result. So the characterization of when Leavitt path algebra is strongly graded has been known. in terms of graph. So a result of the type Leavitt path algebra is strongly graded if and only if graph is such and such, that has been known. But we actually got characterization via monoid using this comparable periodic type of considerations. So what is, by the way, strongly graded? It's your ring chopped in pieces, right? Which are in a way very nice and regular. In a way, they're all kind of just like the 0th piece or being repeated all over and over again. So so let's now let me just now talk about some ideas for the future. Let me relate this conjecture with some others, and I think that that will be it. I'm still good for another like 2 to 5 minutes, Jean.
Yeah, 2 to 5 minutes is fine.
Okay, great. So, these 3 classes that I told you about, periodic, aperiodic, incomparable, in a way match the comet part. Comet is when you can get to a cycle without exit. Rows, which have exits, and incomparable is kind of like the acyclic part. So it's not just that every element is in one of these 3 classes, but if you have a sum of bunch of elements, in a way you can kind of find the largest periodic summoned and the aperiodic and the incomparable parts. So such decomposition can be done, but the uniqueness is a problem, especially if you go to K0 there, right? If you complete. So if that goes, then everything will go very nicely. But that still didn't go just yet. So, and I also need to mention that I talked only about the weaker version of the conjecture, really. The stronger version would be saying that K0 gamma is full and faithful functor. And in fact, the strong version was shown for polycephaly and row, finite, no exit, etc. graphs that I mentioned before. So there is this stronger version also. Now let me relate it to another conjecture, which is the isomorphism conjecture, conceived by these 2 people now in the same institution, yay. And they formulated it for Leavitt path algebras over complex numbers because they wanted to relate it to C-star algebras. In this case, you know, your coefficient field should be complex numbers. So the original version was these Leavitt path algebras are isomorphic as rings if and only if these 2 things are isomorphic as star algebras, right? And since this implication always holds, if Leavitt path algebras are isomorphic as star algebras, then we know that C-star graph C-star algebras are isomorphic. So then you can replace this part here with that part there. So the question is it as rings if and only if as star algebras, right? And then you can remove the complex numbers. And if you want, you can remove the star and wonder just if 2 Leavitt path algebras are isomorphic as rings, if and only if they are isomorphic as algebras, right? So now let's go to graded version of that, right? So the graded version would be asking if they are isomorphic as graded rings, is it equivalent with them being isomorphic as graded algebras? So if graded classification is true, then this conjecture, graded isomorphism conjecture in front of us is also true. And let me just give you a quick like proof. So one direction here is trivial, right? If they are isomorphic as graded algebras, they better be isomorphic as graded rings. So the only interesting direction is this one going down, right? So if they are isomorphic as graded rings, then their K0th, gamma K0th are going to be isomorphic. And if graded classification is true, that will automatically give us that they are isomorphic as graded algebras, right? So that's how these 2 conjectures are related. So, talented Mr. Monoid, I'm done here.
All right, thank you very much, Leah. If all of our participants would be willing to unmute themselves, we can give Leah sort of a general thank you round of applause here for a really nice talk. Thank you. Well done, Leah.
Oh, thank you.
And I can open the floor or the Zoom meeting to any questions anyone might want to pose.
Yeah, I have one question. The Rose graph is essentially a special case of the so-called extreme cycle.
Uh-huh. Oops.
Means simply a cycle which has an exit. If it has an exit, then the range of that exiting edge again comes back. So there is a path from the range of that extreme, the exit edge back to the graph.
Mm-hmm.
So if that happens for every possible exit in a cycle, that's called the extreme cycle. One of the natural question would be, in view of Bayes' theorem, the polycephalic graph, whether if the same thing can be extended to the case when it is just an extreme cycle, the graph is just.
Yeah, that's a very good question.
And the motivation for that is, if E is a finite graph, or if it's a graph having only finitely many vertices, then every vertex connects to either a sink or a cycle without exits or an extreme cycle. So this would be a first step in extending it to the case of a graph with finite many vertices. So
Yeah.
I was wondering if anything was done about extreme cycles.
No, not yet.
No. Hmm.
So that means that if you want to do something about it, I'm I'm going to be right behind you.
Thank you.
Let's see, Efren has his hand up. Efren, go ahead.
Hi, I have one question and one comment, I guess.
Sure.
The comment is actually a question as well. But
Okay.
so the first one is so in graph C-star algebras we have this Kuhn splice where we add in the two vertices, add loops to it, and they connect to each other, and then they connect to a vertex in the original graph. Is it easy to see that they're graded distalented monoid are different?
I don't know. I really don't know.
Okay.
Rubric, I don't know if you know.
I suspect they're different. I just didn't, maybe we just got to sit down and compute the monoids and see that they're different, but I would suspect that they're different. And I guess my other comment is in terms of the conjecture, the graded version of the Abrams-Tomford conjecture. So you could actually also say something about where the Leavitt path algebras are graded isomorphic if and only if the graph C-star algebras are gauge invariant.
Yeah.
Isomorphic.
That's right. Mm-hmm.
Is there anything known about that other than the ones that we already know that they have classification of? But that was just my comment.
Thank you.
Thank you, Efren. Other questions or comments, please? I have a quick question then. So this talented monoid, it's able to recognize a lot of the structural properties of the graph. For example, can it recognize the GK dimension of the Leavitt path algebra? Somehow can it recognize the sequences of cycles and how they connect to each other?
I would say yes. I mean, definitely it can recognize whether the cycles are connected or not.
I see. Okay, so maybe so. Okay.
Not just that, but the length of the path that
Oh, I
connects.
see. So very talented.
Yeah, yeah.
All right. Any other questions for our speaker?
Where'd you get those lovely illustrations?
Which one?
That's
Different
great.
places. The apples and the watermelons, just random apples and watermelons from the
Oh, that's wonderful.
from the web.
You had a knight slaying a dragon. No, that's wonderful.
The ring is from Lord of the Rings.
Oh, okay.
It's a steal from the movie.
I think that anybody who thinks math is dull, I'll tell my wife that I saw this illustrated talk.
Yeah, with Axl Rose. Next time, Leah, you can put in Pete Rose, the baseball player.
Okay.
No, you don't want to be Pete Rose.
No, well, or Axl Rose either. So, all right. Any other questions or comments?
How's things in Philadelphia?
Going okay.
That's the way it was when I was a kid. Pretty bad. It's always the same. People are committing crimes and the cops are beating up people. It hasn't changed in 50 years.
Yeah.
Okay, enough of that.
All right, let's thank our speaker one last time here.
The Phillies are still losing.
Yeah, that's also true.
Phillies are still losing. That's right. So I'm going to quit the recording here.
Okay.
And anyone that wants to stay on and just chat, please feel free to do so. I can stick around for another 10 or 15 minutes or so, and then I can hand it off to anybody that would like to stay. So thank you for attending. Please remember that we'll have a talk 5 weeks from today. Ben Steinberg will talk about Cartan pairs of algebras, and I will send out the standard info on Monday, April 19th. So thank you everybody for participating, and we hope to see you in 5 weeks, if not sooner.